The goal of this presentation is to provide an explanation of 3 different methods for finding the kth smallest element of a collection of integers. We will analyze asymptotic complexities and report on the efficiencies of each method. As I said, the problem we are solving is to find the kth smallest element in a given collection of integer numbers. The collection we used is a file containing 1 million integers ranging from 1 to 1,000. We will focus on the efficiencies for k values of 1, 100,000, and 850,000 in order to compare the 3 different methods. Method 1 uses a heap data structure. A minimum binary heap is a binary tree with a key in each node that satisfies the following 3 conditions. 1. All leaves are on at most 2 adjacent levels. 2. All leaves on the lowest level occur to the left and all levels except the lowest one are completely filled. 3. The key in the root is less than or equal to all of its children, and the left and right subtrees are also minimum binary heaps. To the right, you can see an example in the shape of a tree and also with the values saved in an array, which is how we actually work with heaps. In order to build our heap, we need to understand a procedure called heapify. Heapify takes an element, such as 9 in the diagram below, whose 2 children are each binary heaps, and bubbles down the 9 to its proper place. This turns the element plus its 2 binary subheaps into one heap. To build our heap, we first enter our 1 million integers into an array that represents a heap in the order they appear in the file. We then call heapify until our elements satisfy the heap requirement that each node is smaller than the nodes of its subtrees. This means calling heapify on half of the elements of the heap. Starting at the back of the array, we see the first element with any children is the middle element of the array, so this is the first element that we must call heapify on. We call heapify on that element and then each element in front of it until we reach the first element. Each call to heapify takes at most big O of log of n time, since log of n is the height of the tree, and this is the most times each element can be bubbled down. We do this n over 2 times, so it seems that this whole procedure takes big O of n log n time. We can actually use the fact that many of the elements we call heapify on will not actually take log of n swaps to bubble down. We can get a tighter upper bound using this information, giving us an upper bound of big O of n. When we find the minimum value of the heap, we want to extract it from the heap so that the next call to minimum gives the second smallest value. When we extract the second smallest, the next call gives the third smallest, and so on. So, to do this, we replace the minimum with the last element of the heap, and then call heapify on that element to move it to its proper place. This takes big O of log of n time, since that element may need at most log of n swaps to get to its proper place in the tree. When we find the kth smallest value, we build our binary heap using heapify, then call the minimum function k times. As we said, using heapify to create the heap takes big O of n time. Calling the minimum function k times takes big O of k times log of n time. So our total time complexity is big O of n plus k times log of n. Here you can see how long this method took for k equals 1, k equals 100,000, and k equals 850,000. As you can see, as k increases, so does the time that it takes. This makes sense because k is present in our asymptotic complexity, multiplying the log of n terms, which means as k increases, so will our complexity.